we're going to go to something similar to this. Just bear with me for a moment, because the flipping of the papers makes me a little crazy. So let me get to where I'm going, and then we will, I guess I have to get here. Okay, let's go to the radiocarbon tracer. So you have this slide. I'm going to show you a source apportionment of CO2 that comes from different types of fuel. And a bunch of you talked about that in your group. And I'm going to cheat, and I'm going to use some radiocarbon, even though this is the stable isotope ecology class. There is another class, and it's modeled after IsoCamp, and it's just on radiocarbon. It's only 1 week, because it's just one boring isotope. But it's usually done at UC Irvine. They have an accelerator mass spectrometer that can measure radiocarbon at natural abundance, very similar to this class, modeled after this class. So I'm not going to speak up about this at length, but if you're interested in fuel, especially carbon, and you're in a city, you want to try and add some radiocarbon to your arsenal. And combined with stable isotopes, it's an amazing tool to look at CO2 sources. So radiocarbon has this annoying habit of being radioactive. And so it's the units that are used to express radiocarbon concentrations are a little bit different than stable isotopes. I won't get into the details, but just to flag this in your head, a capital delta is used for C14. It doesn't mean the same thing as the capital we use for delta C13. And we have to do some funny things like correct for the decay of the standard. So the standard used for radiocarbon is this extract of a sugar beet crop from 1950 or 1955, and you have to account for the fact that your standard is always decaying. So there's a correction for that in here. And then you do this really weird thing. It's really hard for stable isotope people to accept, which is that you get rid of mass-dependent fractionation. You correct it out. Because when you're using radiocarbon, you're interested in the decay. And the fact that, let's say, a plant discriminates against C14 is not of interest to you. So all standards are corrected to a stable carbon isotope ratio of -25, which I know sounds like a really weird thing to do. But if you start to dig into the use of radiocarbon, it will make sense. Why do we love radiocarbon so much? Because how much radiocarbon is present in fossil fuel? None. It's because the half-life of radiocarbon is relatively short, and it's all decayed away by the time you put gas into your car. And that's really different than the modern atmosphere. And in fact, if you were to sit with these units and embrace these units for a while and feel the units, then what you would get is the modern atmosphere has a radiocarbon ratio of 50 per mil, and fossil fuels are -1,000. And that's such a huge difference that it's so easy to find fossil fuel CO2 wherever you're looking. The atmosphere, a plant, an animal, you can always see it because you can actually resolve 1 ppm, which is not very much, of fossil fuel CO2 pollution because a 2.8 per mil depletion is resolvable with an accelerator mass spectrometer. And that's why we love it so. So I'm going to put that tool in your arsenal, and I'm going to fast forward to another graph. So just bear with me before you start turning the pages. We're going to fast forward. We're going to go past these really pretty maps, which in spatial, we'll do the maps, the other isotope class, and I'm going to take you here to this funny looking thing. So this is what you want to think about if you're doing pollution sourcing. You need to take a look in isotope space of the isotope ratios, hopefully multiple isotopes, 2 isotopes. This is 3 isotopes. CO2 has 3 isotopes we can easily measure: carbon, stable carbon, the good carbon, oxygen, and radiocarbon. So we've got 3 possibilities there. Got to make sure that your pollution sources have a unique combination of isotope ratios, and that will let you do your sourcing. So for CO2, and we've spent a lot of time thinking about CO2 here at the University of Utah. Jim has created a gigantic operation to sample urban CO2 here. And here in the Salt Lake Valley, the CO2 sources are distinct for three things that are major sources of CO2 locally. The combustion of natural gas. You guys talked about the fact that natural gas is burned for fuel. Here in the Salt Lake Valley, it is the most common source of heating fuel, and so there could be a lot of it in the atmosphere. Gasoline, of course, from your car. And respiration. It turns out, as you'll see in a moment, there's not an insignificant amount of biological respiration in the urban atmosphere, especially at night, when there's a big gross flux from ecosystems to the atmosphere, meaning that there's no photosynthesis to suck up biological production. And so all of that soil, the plants, and humans, but it is mostly plant and soil respiration, are there in the atmosphere at night. Could be a lot, and isotopes will tell you that. But there's a funny thing about gasoline combustion. It's a little bit annoying. It has the same isotope ratio, the same carbon isotope ratio as biological respiration. Because where does gasoline come from? In geologic history, what was gasoline? It was a plant, stable carbon. So it still has that plant carbon isotope ratio of a C3 plant. And so stable carbon alone, it's tricky. If I burn wood in my fireplace, if I burn gasoline, and if I respire, if I'm a plant respiring, that all has the same stable carbon isotope ratio. Can't tell the difference with stable carbon alone. Does that make sense? That's why we want to add more isotopes to make this work. So natural gas does have a very depleted carbon isotope ratio because of the thermogenic processes that create the natural gas that's mined for fuel. If you want to distinguish the biological respiration from combustion, we can add in oxygen isotopes. Oxygen isotopes, the mechanistic basis for this will have to be covered in one of the other lectures, so I have 5 minutes. And oxygen isotopes are a little tricky, but the easiest one to wrap your brain around is the isotope ratio, the oxygen isotope ratio of combustion. Because where does the oxygen come from in CO2 that was produced from combustion? Comes from diatomic oxygen, O2 in the atmosphere. And that isotope ratio is transferred over, more or less. There could be a little bit of fractionation there, but it's not that dissimilar. So the isotope ratio of combustion for oxygen, we know. It's going to be really similar to O2. For biological respiration, this will be the subject of some wonderful lectures later on in this class. It depends on how plants and soils have equilibrated with liquid water. That will impart an isotope ratio onto CO2, and you're going to learn more about that a little bit later. But these are the reasons why these things tend to be isotopically distinct, but you need to check the isotope values in the local ecosystem where you are. And we have done a lot of things here, like going to the crude oil facility where they refine gasoline and got some samples and measured them, and many long and sordid stories about sticking sampling tubes up the tailpipes of cars and things like that. So these are local data from Salt Lake City. Okay, so if you have that information, now you want to use it. And so this is the CO2 concentration over this building in the year 2002. Which is the year that the Olympics were here. They were right here on campus. It was really cool. And this was the CO2 concentrations in that year. So the average daily concentration is the thick black line. The dashed line at the top is the maximum for that day. And the gray line is the minimum for that day. You see this huge seasonal pattern. Highest concentrations in the winter. Why is that? It's something special. That's just, we're special here in Salt Lake. The inversions. We have horrible pollution in the winter for atmospheric reasons, and which happened to correspond with the Olympics, gave us very bad reputation because it was all over the media that we have this terrible pollution in the winter. So look at the concentrations, the numbers on the y-axis. The background, wow, look how the background has changed since we did this study. The background's much higher than this. But back in those days, it was about 370 ppm. Now it's over 400 ppm. But in the winter, the local concentrations here were going to 550, 600 ppm. Since this time, we've seen 700 ppm here in the winter. Big local sources from urban combustion. So everything above that purple line is local CO2 generated by the city. And the question is, can we figure out where that CO2 came from? And we can because of this graph. So these are more equations for you to ponder on your own, but this is a very simple mass balance problem. If I take, let's say that this water bottle was just full of air, and I want to know where did all the CO2 come from that was in this water bottle? Well, it's mass balance problem, because we're going to account for all the CO2 in the bottle. So there's going to be the total amount of CO2 is on the right there. And now we want to say, if we have accounted for all the major components, problem has to have mass balance. Dave Bowling is going to tell you all about this wonderful field of figuring out CO2 mass balance. So here, we're going to just write 3 equations. The second 2 equations are taking the isotope ratio of each component and multiplying it through. The top one is just saying that the total amount of CO2 in the air has 4 components. If we multiply every single concentration by its own isotope ratio, that's the second equation, still preserves mass balance. Third equation multiplies each concentration by its own oxygen isotope ratio, still preserves mass balance. 3 equations, how many unknowns can we solve for? 3 unknowns. And so that brings us to the punchline, which is taking the total CO2 concentration that we measured over this building and partitioning it into its component sources. It's basically just plugging all the known isotope ratios and the total CO2 concentration into those 3 equations and solving it. And you can get this kind of a thing. So this shows us that in the winter, natural gas combustion is super high. Makes sense, because it's used for heating. And in the summer, you get this biological component from respiration. Makes sense, because in the summer, plants have leaves, it's warm, and the soil is respiring. So these basic patterns make sense. And this was the first study that we did using this method in 2003. And since then, we've refined this method quite a lot. So if any of you actually want to do this, then let me know. And we can go over the various iterations of this. Probably the best way to approach this problem is not with an analytical solution, but with a Monte Carlo simulation, where you can account for uncertainty in each of the parameters, which means you can run these equations. You can solve these equations 10,000 times, and then you can actually solve for more than 3 unknowns, because you can get a range of possible solutions that has a probability distribution, and then you find the most probable solution. Does that make sense? So that's the way I would do it these days. So this was just a little taste into things you can do with isotopes in cities, and there are many, many, many more, and the literature is wide open on this. So let me know if you guys have any questions, and I will see you all tomorrow.